Last time we learned how to implement Euler's method. We wrote down our code using the for loop. Let's quickly review that. Let's take a differential equation x dot equal to minus 2x. We want to find x as a function of time, and we use the initial condition that x at t equal to 0 is 1. So therefore we define the derivative function, that is x dot equal to f, as f of t comma x is minus 2x. F in general can be a function of both t and x. In this case, special case, it is only a function of x. So we defined f of tx equal to minus 2x. Then we initialized certain variables in our code. X initial equal to 1, t initial equal to 0, t final equal to 10, and we decided n max equal to some number of steps. Let's start out by, let's say, 100 steps, and then we calculate h as tf minus ti over n max. H is the step size. We evaluated this, we got a step size h equal to 0.1. This is the only statement we are printing, the others are suppressed. Then we wanted to generate a solution in the structure of set of points t naught, x naught, t1, x1, t2, x2, and so on. So in order to do that, we wrote a for loop, and this is the condensed version of the for loop that we came down to, starting from a longer version. So what did we do in this for loop? We initialized data list. The first element of data list is tixi, so we created a data list and inserted the first element in tixi. This was the initialization step, and that was the only initialization step that was required. Then we went ahead and put the condition that I want data list, the size of data list, to be less than or equal to n max, because there are n max number of steps. So we said, in fact, it should be n max number of steps, so size of data list should be n max plus 1. So let me add 1 over here, because the size is already 1 and there are n max steps, so total n max plus 1, the size will become n max plus 1. So length of data list is less than or equal to n max plus 1. That is our condition to stop the for loop. As long as this condition is true, for loop will continue to execute the body. The next statement is the increment, but increment is always done after the body is executed. So in the body, we only wrote down one statement, that find the previous step. Previous step is the last element of data list. In this case, when the for loop begins, the last element of data list is just initial value tixi, and after the body is executed in the for loop, we are going to increment. Then in the increment step, we increment to data list the next step, and the next step is evaluated as previous plus the time component is h. In the time step, we add an h. In x, we step h times f acting on previous, that is a derivative, f is a derivative, f acting on previous. To quickly remind you, remember the previous is a set of points for something for time, let us say 0.1, and something for x, let us say 2, and we are doing f at. So f is send the two arguments, in that is the first element of the list and the second element of the list. The first element becomes the time and the second element becomes the x, and f is passed these two arguments, and f evaluates to the value. Remember, f was minus 2x, so minus 2 times 2 is minus 4. So that is what this does, multiplying it with h. H in this case is, multiplying this with h gives me the step size in x, the increment that is to be made in x, and adding that to previous gives the adding h comma h times f added previous to h increments both the time and the x simultaneously. So we have done quite a bit in this increment statement. We have calculated the next step, added it to the previous, and appended that entire thing to the data list. So now this becomes the last element of data list. The next time when the body is executed, the previous becomes the last, so the next step of this time becomes the previous for the next time. And in this fashion, for loop continues till n max plus 1 steps, and we are going to execute the for loop now. This is done, and if you want, you can print the data list. This is my data list. Let's go ahead and check the last element of data list. The last element of data list is 10.1, So, I must have made a logical mistake because I wanted to calculate to final time Tf equal to 10. So, I think this has to be n max. Okay, let us go ahead and do this again and check the last element of data. Is that is correct? It is now turning out to be 10. So, you think about this counting. I will move forward and we will go ahead and make a plot. So, I make a data plot for this and I get this plot. I make the solution plot for the function, the expected solution e to the power minus 2t, and I get this result. I can show them on top of each other and you see there is some difference. We want to, so we are getting this shape of the solution but not quite write the solution. And the reason for that is that step size is too large at this point. The black is the solution, expected solution of the differential equation, and blue is the numerical solution that we have obtained. So, let us go ahead and make the h smaller, and we have done this last time. Remember when we made h further smaller down to let us say 500, and max equal to 500 makes h equal to 0.02, and then we executed for loop, and then this statement I do not require, so I will delete it. And when I did this, you saw that there was a significant improvement in the solution, but you see still that there is a minor difference, and in order to improve that you may probably want to go to a higher number of n max, maybe 1000, and we can do this again, try this again to even get higher accuracy. You see that there was some small change in this number that happened. This is the last value of the data list. So, let us go ahead and do this again. There was some small, very small change. Now, let us go ahead and do this now again. Now, you see there is a perfect agreement. So, in order to get this perfect agreement, we had to go down to a very small value of h equal to 0.01. Let us go ahead now and understand how we can, what is the impact of h on the quality of the solution. So, without proof, I would like to tell you a little bit about importance of h when you are doing the Euler's method. Remember that we wanted to find the solution from time some t0 to some time tf, or this was ti and this was tn plus 1, and we divided this time axis into small tiny bits. Each of this was delta t or step size h, and we use Euler's method to do the integration. That means delta xi was calculated as f evaluated at ti minus 1 xi minus 1 times delta t or h. I should write h because that is what we have been calling. So, this is h. Now, so question is, what is the size of the error? What is the size of the error that is? So, we are getting xi's by doing this process by building up steps. We are getting an xi, and we have got a solution from the integration, that is we have obtained solution x as a function of t. So, from this we can obtain what is x of ti. This is the true value of x from the solution, and this is the numerically obtained value of xi. Since we are making increments of step size h, so our accuracy will be h, therefore the error will be order h square. So, I expect that x of ti minus xi, this should be order h square. So, let us go ahead and validate this numerically. Now, the solution, the problem that is at hand is x dot equals minus 2x, and the solution of this is x of t equals e to the power minus 2t. Of course, we have used the initial condition x at 0 is equal to 1. Okay. So, therefore, I have obtained, I know the solution. So, I will substitute ti in this, and that will be my true value of the solution, and the expected value is something that I have obtained numerically. So that's what I want to do. So let me go ahead and try to do that really quickly, and what I'll do is I will add over here, I'll take data list and I'll take a certain point in data list, let's say the 20th element in data list is has t equal to 0.19 and the x value is 0.68. So now I will take the first element of this 20th element, that is 0.19, and I will calculate my true value by multiplying -2 to this, that is e to the power minus 2t, and that is 0.68. To this I will subtract the obtained value, which is the data list, the same thing, 20, and the second element of this. Okay, so let's just first compare them. So in order to compare them, I'm gonna put them in a list. So the first item is the true value, and the second item in this list is the calculated value or numerical value. So we see these are pretty close, but there is some difference between the two, and I want to understand what is the difference. So therefore, in order to understand that difference, I will take a difference of these two numbers and I will calculate its absolute value. So I'll do a postfix abs is for absolute value, it's going to put a mod on that, and I get a number 0.002. Now you see that this 0.002 is for the 20th point. So what I want to do is, now I want to make this arbitrary, so let me call this as n and call this as n, and I will put this inside the table, and I will run n from 1 to length of data list. So length of data list, and that will give me all the values of this difference, the absolute values, and here is my entire list. And what I really want to do now at this point is, you see all these numbers are comparable. See that they starts out from some really small value, but slowly builds up to 0.001, then 0.002, and then eventually it remains of that order. So I want to get a fair estimate of, you know, of the size of the error. So what I'll do is I'll calculate the mean of this whole thing. So this data, this list that I've obtained, this data I've obtained, I want to calculate a mean of that, an average. So I'll apply postfix mean function on that. Mean function will give me mean of all of these values, and there we go. The mean that we obtain is 0.00005, and let's go ahead and compare this with h. So the h value, so the h value I have is the h value I have is 0.01, and I said the error average is going to be order h square. So and you see that it's of that order. And the fact that it's 5 times higher is very specific to the problem. The point the point over here is that we use the Euler's method. We moved in step sizes of h. Euler's method tells us that errors are of the order h square. We are not giving you a proof of that. We are just giving you that this is the case with the Euler method. We get an error of order h square. So therefore, we calculated the average error from all the calculation we had, and we found the average error was 0.00005, and when we calculated h square, we found that number was comparable. In order to verify this, let's go ahead and rerun this entire thing, and in this time we are going to change n max, and that's going to change h. Now my h is 0.1, therefore my error should become larger, it should become of order 0.01. So let's go ahead and find that out. So I'll execute this for loop again, and I can do the data plot again, and you will visually see the difference. and you can, from here you can estimate the difference visually. If you move in a line vertically up, you do see that the error is of the order of 0.01 approximately. If I move along this line up here, the value here is 0.01 on the blue curve, and on the black curve it's about 0.02, maybe slightly lesser, but then we are making a ballpark estimate. So the error is about, the difference between them is about 0.01, but let's go ahead, and that's for one point, but we want to calculate a mean for this entire range. So let's go ahead and execute this statement again, which should give me the mean, and we do see that it turns out to 0.005 and h square is 0.01, so it's about half of that. So we found that in this case expected size is 0.01 multiplied by an order 1 number can happen. It's not going to be exactly h square, it's going to be order 1 number times h square. In this case, that order 1 number turned out to be 1/2. We can go ahead and re-evaluate this for a different value of h, and I will invite you to play around with this. So let's go ahead and make it 500 and run this again, and we don't need to execute these statements, and we can go ahead and execute this one over here and execute h square, and you see that again we find that the mean error that we found in this is comparable to order h square. So that validates the point that when we are using Euler's method, the error is order h square. Let's go ahead and improve this. You see, we have been going back and forth again and again to execute all of this, but if you want to do a thorough study, you may want to construct one single function in which you can do all of that. So what we'll do now is we'll turn this for loop into a function, that is our Euler's method into a function, and for this we'll use module construct. If you have not watched my video about module construct, that is the technical problem 5, please go ahead and watch that, because in this now we are going to use the module function to construct, we are going to turn this into a function. So let's go ahead and do that. So I'm going to add a title over here. So Euler's method as a function. I'm going to write Euler's method as a function. I'm going to call that function as Euler. The name of my function will be Euler. All the custom functions or custom variables that I define, I always start with a small letter such as small e over here, because block letters are used for defining built-in Mathematica functions. I don't want to run into any conflict, so I always define my own functions with small letters, and that's the policy I'll use over here. So I want to define an Euler function, and to this Euler function I want to take some inputs such, and my inputs in this case are going to be the initial time ti, the final time tf, initial value xi, and I want to give the function, that is the derivative function, that is x dot equal to f of x. So this is my input. Let's see what else do we require. So here's what our inputs were for the for loop: xi, ti, tf, and max. So n max we want also as an input, which tells me how many steps I want in order to do my evaluation. You can use n max as an input, or you can use h as an input, but I usually like n max as an input because I fix my final time. I don't want to change my final time by defining n max and h. I fix my final time, I decide n max, and from that I calculate h rather than using h to calculate n max. But you can also take another approach if you want. And I want to do a set delayed over here, so colon equal to, and I want to define my own function, so I'm going to use the module construct. And this module construct I'm going to have two parts. One is the local variables and others is the body. So I'll write the local variables and different statements of body in different lines. So these are my local variables. So for illustration, let me put that comment over here. This is local variables which are only visible inside the module function, and in the body, so this is going to be my body. There we go. And the first thing I want to do in the body is I want to calculate h. So I want to define h as a local variable. Remember that there was one h already defined, which is a global variable, but now I want to define h as a local variable. So I will put a h inside the first argument, and that becomes a local variable. You see there is a color change, and now this h is going to be tf minus ti divided by n max, and we will do a /n, so that it's evaluated to approximate number, so that the computation is fast. And there's my body, and then I'll go ahead and write other statements of the body. And this point I want my for loop, so I'll just go ahead and copy this for loop and paste it over there. Now you see that this for loop also has some variables inside it, and I'll have to declare those variables as local, so that they're not affected by the global values. I'll go ahead and call data list also as a local variable, and you see the moment I do that, there's a color change over here. And then there is a previous and f, and clearly this f has to be the local variable function that I'm passing, and I want to define one more local variable, that is previous. And now I think this is done. I'll end this for loop with a semicolon, because I don't want any output from that. I just want to run that for loop, and then I'm going to return data list, the local variable data list that is part of this module. I want to calculate that data list, append information to that data list, and I want to return that data list. And this way I've constructed a function Euler, which takes the input ti, tf, xi, the function that I want to pass on, and nmax. So now I can go ahead and execute this, and you see when I execute this, nothing happens, because this is just a definition. I made a definition that I've made a SetDelayed definition that I'm going to execute this when I call the Euler function with certain inputs. So until unless I call Euler function, this is not going to happen. And when I'm going to call an Euler function, I'm going to call it with certain ti, tf, xi function and max. Alright, so let's go ahead and do that. So for this purpose, I need to define a function. So let me call this ff this time. Let me call this f1 of t comma x equal to, and I'm going to call this minus 2x. This doesn't really matter. I can make a SetDelayed definition or a set definition. Let me make a set definition. There we go. Now I want to call my Euler function. So I want to call my Euler function with the input. So my ti was 0, tf was 10, xi was 1, that is at t equal to 0, x was 1. To the function I just want to pass the name of the function f1. Note that over here I don't need to pass the argument, because arguments are being applied over here. Here I just need to pass function as a symbol. The function as a symbol is the argument for this, so I just need to pass f1, and this f1 needs to be defined, that we have already done. And then I want to decide nmax equal to 100 points, let's say, and I want to execute this. The output of this should be data list, and that's what I got. I can go ahead and do a list plot on that, and when I apply a list plot to that, this is what I get. Okay, let's go ahead and do this. I'm going to call this my data equal to Euler. So that's one statement. In the next statement I'll do a list plot. In this list plot I'll say my data, and then joined is true. Let's go and execute that. This is what I get for my plot, and I want to compare this now with the solution. So the solution was, I want to enclose all of this inside the show function. The solution was e to the power minus 2t, and t goes from 0 to 10. There we go. I can change the colors, make this red, so that we can differentiate. So that is my expected solution, and this is my calculated solution, and I want to improve this, so I can just go ahead and change Nmax, and now you see this has been defined as a function, so I can go ahead and simply call the function and improve it. I can further improve it by changing Nmax. There we go, and if you want to further improve it, maybe I can go to 1000. There we go. So this Euler function we have defined as a function, and with a single call I'm able to do all these 5 or 6 different steps that we were doing before. Let's go ahead and do one more thing. We are going to define an error function to calculate the error that we calculated over here. This was the error that I was calculating, mean absolute error. So in order to do that, I'm going to define a function that is an error function. So I will define another function. I'll call this function as error, and it has gonna be 2 arguments. The one argument will be the data that I'm going to pass to it. That data will be in the same structure as my data list, and I'm going to pass it another function which is the solution function. So I'll call it as solution function, which is a function of t, so that I can find the difference and compare, and I'm going to write this as a module again. So what I want to do here is again define a set of local variables and then the body in the next line. So I want to define over here what I want to do is I want to define variables t-list and x-list. So x-list is going to be, so for t-list I'll extract from my data the first component of it. So I'll take all the rows, so double semicolon means all the rows of it, and the first element in each row, that is all the times, and I'll get the x list, and that will be, in order to obtain the array element, I press escape, press 2 square brackets, press escape again, that becomes a double square bracket, and then I do the same thing to close it, and that becomes that can be used to determine the array elements. I think we've done this before, but just to remind you, again we'll use double semicolon to get all the rows and the second element. For this, let's see if this is what is going to give me expected result. So let me just go ahead and return t-list. I'm not done with the function yet, I'm just building the function, so I want to test it out step by step. So that's going to return me t-list. Let me go ahead and print the t-list now to see if this is what t-list was supposed to be. I want to call error function with the data, my data, and some solution function which have been not defined, so I'll just go ahead and pass f1 to it. Doesn't really matter. All right, so this is, it has taken my data and extracted the time part of it, and I can go ahead and check for xlist also. So if I make it xlist, just taken the data and extracted the xlist, the x component of the data. All right, so that's what was intended. Now what I want to do is I want to calculate another quantity called x true, and this is going to be my solution function, which is a function of only t. I want to apply it to each value, so I'm going to use the map operator /add of t-list. So this is going to give me, I'm going to apply solution function at each element of t-list. That will give me a list of true values of x that is expected. I want to define x true as a local variable. Let's go ahead and check that I'm getting some expected result. So let's go ahead and return x true from here, and let me, in order to pass this time, I can't pass f1 because f1 is the derivative function, not the solution function. It has two arguments. Now I'm actually using solution function, and the argument of solution function is a single element, each element of t list. So I should define that. So my solution function is, which is a function of t only, is e to the power minus 2t, or exponential of 2t. So that's my solution function, and I want to pass this as an argument to error function. Let's go ahead and do that, and there we go. So that gives me exponential e to the power minus 2t applied on the times. Alright, so what now I want to do is, x list is the calculated values, x true is the true values of x, and what I really want is take the difference of the two. So when I take a difference of two arrays, I'm going to get difference of array of difference of elements. So I can go ahead and directly do that. I can go ahead and directly do x true minus x list, and to this I can apply postfix absolute value and postfix mean, and that'll give me the mean value. Now I can do this very quickly with experience, but if you're not entirely sure, you can go ahead and do this step by step, make the checks in between that are necessary for you to do, just like I printed t list or return t list and return x list and return x true to verify that I was getting some expected results. You can make stronger verifications by evaluating some of the numbers on a calculator or separately over here and comparing them. But if you're experienced, you can actually go ahead and directly do this thing, and let's go ahead and do that. So this is my definition. So now I'm going to get, now my error function is going to give me mean absolute error returned, and let's go ahead and check that. So I'm going to get a single number, and just to verify that from our older code, that when I had 1000 points, this is the error that I got. So let's go back to our older code and make this as 1000 code, just to verify that our error function is actually giving what we did before. So let me go ahead and calculate the error from this statement over here. There we go. This is 0.005, and over here it is again 0.005. Very good. So now what we have done, we've got two functions. One is the error function, and the other one is the Euler function. We have defined two functions over here, and we'll keep on using these functions again and again for testing the calculations that we're making. So let's go ahead and combine this. So I'll just copy this and put this right over here. Now I can go ahead and combine this statement also over here. So I'll define f1 of t and x, that is my derivative function, as minus 2x. The solution of this equation is the solution function, which is a function of time only, and I'm going to define that as e to the power minus 2t. Now I'm going to call the Euler function to calculate the solution, and then I'm going to call the error function to go ahead and calculate the error. So for this I'll pass it arguments my data and solution, that's my error. Let me not put a semicolon because I want to print it, and then over here I'm going to do a show of list plot of my data, and this is the solution function. So let me replace this e to the minus 2t by solution function of t, and this is my ti from 0 to f. Let me go and execute all these 5 statements in a single go. seems like this. Oh, error is the function, so it has should have an argument. There was a typo there, and I want to go ahead and execute it now, and there we go. So we have got the error over here and the comparison of the two plots, and now you can go ahead and play around with this. You can make it 100. The error changes, and you see the comparison over here also changes. I can make it even worse, make it 10, and you see I really get a bad result. My error is order 1, and I'm getting a really oscillatory kind of solution, which is completely unexpected for this. Of course, that would happen if you make nmax very small and h very large. So in order to get some reasonable value, we should make it larger. So 50, you see that the error is 0.01, and the difference in the curves is visible over here. Now we can go ahead and play this around with for some more functions, some more other known functions. Let's try f of tx as, let's say it is cos of t. And you know the solution of that? Solution of that is sine of t. So if x dot is cos of t, the solution x of t is sine of t. Given that the initial condition is at t equal to 0, x is also equal to 0. So that is my initial condition. At t equal to 0, x is equal to 0, and I am calculating to final time tf. Let's go ahead and do this with 50 points, and I want to, let's go ahead and execute that. There we go. We get an error of 0.1, mean absolute error of 0.1, and the red curve is the true solution, black dots joined together is the calculated solution, and you say that they are pretty close, but they don't agree with each other very well. Of course, we can improve it by increasing the number of points or the number of steps in the calculation, and that makes things look a little bit better. We can improve it further. There we go, it becomes even better, and improve it further by increasing more points to get a perfect agreement. So this is close to a perfect agreement. Now you see that the error has become 0.01, and we should probably print also the h value, or rather we can do is we can print error divided by h square. All right, we'll do that later in a bit. So there we go, we have got. Now what we'll do is we're going to go ahead and compare this error. We don't need this. We'll go ahead and create a list of errors. So let's go ahead and go back to, what I want to do is I want to compare error for different values of h. So my h is ti minus tf. In this case, tf is 10, ti is 0, so 10 divided by nmax. Nmax is I want to change nmax. Let's just start with nmax equal to 100. So if nmax is 100, so tf over nmax is h, and to this I want to compare. The error. So error of my data, but my data is obtained by Euler function. So let me go ahead and call this Euler function. Call this Euler function. The second argument is the solution function. So let me go ahead and put the solution function as a second argument, and this is 100, nmax is 100. Let's go ahead and calculate that, and we get 1 by 10.05. So you see this is comparable. Actually, I want to compare this with h square. So this is h. I want to compare with h square. So those two numbers are the same order, they're comparable. And now I want to go ahead and change nmax to 200 and nmax to 200 over here to see if this comparison works. Okay, we get that. Now let's go ahead and make this arbitrary. So let's go ahead and go back to our older function f1 of t comma x was minus 2x, because we studied errors for that a while ago. So let's do that again, and solution function for this was function of t only, and that was e to the power minus 2t. That's my solution function, and initial value of x was 1. So let's go ahead and do that. And now I want to make this automated. So I want to define this as 10 to the power n, this as 10 to the power n, and I want to vary n. So I'll wrap this inside the table, and I'll go ahead and say I want to change n from 1 to 4. So 10 to the power 1, so n max is 10 to the power 1, then next time 10 to the power 2, then next time 10 to the power 3, and 10 to the power 4. So let's go ahead and do that. We are going to get 4 sets of numbers. There we go. So the first time we get h square to be order 1, and we get error also to be close to 1. Next time we get h square to be order 0.01, and we get the error of the same order. Next time we get error h square to be order 0.00, 10 to minus 4, and that's the same size as the error. And next time we get h is 10 to minus 6, and again error is order of 10 to minus 5, or 5 times, yeah, error is 10 to minus 5. So you see that the error does scale like h square. In fact, if you want, you can divide this by h square. That is, I want to divide this by this to see that we get an order 1 number. So now what I'm doing is I'm dividing the error that I'm obtaining by h square, and when I execute that, you see that I'm getting about an order 1 number, but for very small h's, you see that the error is even larger. It's 50 times larger. So at some point the error is not h square, it starts to become significantly larger. Alright, so this was understanding the Euler's method, writing the Euler's method as a function, and understanding the mean absolute error that we get from Euler's function. So go ahead and try out few more examples of this, and you will see that you'll get somewhat similar results. You will find that errors that you obtain will be typically of order h square, sometimes slightly more, sometimes slightly less, depending on the function of the case you are working. But you see the precision of Euler's method is only order h square. Now that means that if I want to get an accuracy of order h square, suppose I want to get an accuracy of 10 to minus 4, that means h square is order 10 to minus 4, that means h has to be 10 to minus 2. So in order to make h equal to 10 to minus 2, I have to appropriately choose n max, that is tf minus ti over n max has to be 10 to minus 2. So therefore I have to appropriately choose n max. Now this makes the Euler's method not very useful, because if I want an accuracy of 10 to minus 6 or even 10 to minus 8, I need to make h smaller and smaller. That means number of steps is going to become larger and larger. So this is the limitation of the Euler's method, because the order is h square. I need to make h smaller and smaller to get higher accuracy. So therefore next time what we'll do is we'll look at improved Euler's method and fourth order Runge-Kutta method, so that we can get higher accuracy with less number of step size. So next time we'll review these methods and we'll see how they improve upon the Euler's method that we have worked out so far. In the meantime, go ahead and try out some examples with this method, write your Euler function, try different cases where you know the analytical solution, and see how playing around with h and max, ti and tf, all other parameters, how does your solution compare with the exact known solution. We'll see you next time.